Let's go over some of the mistakes kids made on the last circular motion quiz. A big one was the graphs, and all we're talking about is graphing this formula. We're talking about an object being swung around in a horizontal circle. Force versus velocity. Well, the force acting on that object is the tension in the string. We're going fast enough so that the mg is relatively small. That's why it says we're going in a horizontal circle. So the force we're talking about is the Fc. Now, what does the force do as the velocity increases? Look at the formula. M and R are constants. The V is getting bigger. It's V squared. The graph has to look like this. Now, if we say, what is the force versus the radius? Everything else has to be held constant then. So really, this could be like a 1. That could be a 1. Does that kind of an equation look familiar? How about y equals 1 over x? If x is small, y is big. If x is big, y is small. I don't think we're asking for too much. Just think about what that means for a second. If you're traveling in a straight line and you have to make a tight turn, that means a small radius. You're going to need a big force. Nobody makes a hairpin turn at 60 miles an hour in a car. Too much force is required. You need a larger radius. What about the force versus the mass of the object? If V and R are held constant, then that's just a 1. That gets bigger, that gets bigger. In other words, we need more force to make the turn. Just a straight line. Now, another problem kids got wrong was the Ferris wheel when it asked for the number of G's at the top and the bottom. That's just the apparent weight over the actual weight. Up at the top, we got the weight going down and the normal force of the floor holding the guy up. The Fc is caused by this weight, and the Fn is going the wrong way. Well, the Fc is the mv squared over r. The v wasn't the problem. People could get the velocity. The problem was getting the number of g's, because I didn't give you a mass. Hey, if I don't give you a mass, and you know the mass doesn't matter, just make it 1 kilogram. Plug in 1 kilogram for everything, calculate Fn. Put it up here, divide by mg. You're going to get the number of g's. Now, what about at the bottom? I don't know the answers to these things. I got to draw the free body diagram and figure it out. The normal force has to be bigger than mg because that's how it keeps us in the circle. So I'll say that the Fc is caused by Fn, but the mg is going the wrong way. It's the same velocity, so we just write mv squared over r, same number as before, and yeah, we're plugging in 1 for the mass again, calculate Fn. The number of g's, it's still the apparent weight over the actual weight. Now, something interesting about the 1 kilogram. Everybody on this ride feels the same number of g's. Whether you're 20 kilograms, 100 kilograms, it doesn't matter. You're going to feel the same number of g's. That's why we can use the 1 kilogram. It just cancels out. How about we talk about orbital motion? You've got a satellite. It's up in outer space. It's got an orbital velocity. But what are the forces that keep it in the orbit? Just the force of gravity. That's it. If it didn't have that force of gravity, it would go in a straight line. But we know it's curving, so there's got to be a force. So we say that the force of gravity is causing the Fc. Newton's universal law of gravitation, the mass of the Earth, the mass of the satellite. Circular motion, that's the mass of the satellite. That's the object in motion. That's its velocity, and this is the radius of the orbit. There's the big news. The mass of the satellite cancels out. So what does that mean? Whatever the mass of the satellite is, maybe it's even a mass of just an astronaut. Whatever it is out there, it has the same orbital velocity. So if an astronaut goes out for a spacewalk, the astronaut doesn't drift away. They stay right with the spaceship because it's got the same orbital velocity requirements no matter what the guy's mass is. So one of these r's cancels out, and if we're 500 kilometers up in outer space, you have to add that to the Earth's radius to put in for r. Better do it in meters. Now, if I'm asking for the orbital velocity, great, you got it. If I'm asking for the mass of the planet, well, then you'll have to calculate that from the orbital velocity. However it works, you got to work with these formulas. Hey, why do astronauts float around inside the spaceship? Is it because there's insignificant gravity out there in outer space? take that formula and divide both sides by the mass of the astronaut, or whatever it is, the mass of the satellite, and you're going to get the gravitational acceleration. You go plug in all your numbers for this, and you're going to find out that G is like 8.5 meters per second squared. If the spaceship was a little closer, it'll even be higher than that. Hey, G on the surface is 9.8. There's no way it's insignificant gravity. Of course there's got to be significant gravity. That's why it's in the curve. If you had insignificant gravity, it would just be going straight. So why do they float around in there? The bottom of the ship is curving with the orbit at the same radius that the astronaut is. There's nothing holding them up. The spaceship falls out from underneath the astronaut. How about a few words on artificial gravity? I'm talking about in a space station. Now, a while ago, I sent you a Word document. It had links to videos on space stations, and I can't imagine too many people watched it, but it is discussed in the chapter notes, and there's a problem in there about it. If you saw the movie The Martian, or 2001: A Space Odyssey, astronauts are walking around on the walls, or at least what appears to be the walls of the space station. But the space station is rotating. So what's going to keep that astronaut in the circle? There's a normal force from the floor keeping her in. That's what produces the FC. The astronaut wants to go in a straight line. That's her inertia. But the wall curves her in. If you're standing inside this thing, you're not going to feel like you're going in a circle. You're going to feel like there's artificial gravity throwing you outward. But that's not what's happening at all. The wall's holding you in. And now for the conical pendulum. That was pretty much a disaster. We did the lab on it. We did videos on it. You did problems on it. You got to be able to do this. Yeah, you have to count the boxes and look at the scale to get the radius. You can count the boxes to get the height. The pivot point is up here where you're gently holding it with your thumb and index finger, not down here at the end of the string. I think you know the free body diagram. It's the weight and then the tension in the string. How do you know what the tension in the string is? You have to read the spring scale in this problem. Now, what is Ty equal to? It's got to be equal to mg, because it's not accelerating up or down. Well, that's going to leave us with Tx. That's what's producing the Fc. So we can say that the Tx is equal to mv squared over r. Now, it's very helpful to know that angle. How do you get that angle? Well, if you counted the boxes over and counted the boxes up, you can get that angle. That angle is equal to this angle. Why do I care? Because opposite over adjacent equals tangent theta. Put the Tx up here. Opposite over adjacent. Well, the opposite is Tx, the adjacent is Ty. Tx is mv squared over r. Ty is mg. The masses cancel, and this is equal to tangent theta. Well, from here, you can solve for the velocity, which you know is distance over time, which is the circumference over the period. Okay, so here you have it all put together. If you needed to know what the weight was, you know this tension. You can multiply by the cosine of the angle to get that. This is the hardest problem on there because of all these steps. Okay, so save that one for the end maybe. Do all the other easy ones. Well, how about the problem like the string with the braking force? This should be pretty easy. But if you don't know what a braking force is, you're in trouble. How much force will this string be able to exert before it breaks? That's what was given in the problem. If the string can only hold, say, 30 newtons, then that's what you put here. That's the maximum force. And that's what's producing the FC. If you know that number and you know everything else, you can get the velocity, you can go get the period, and 1 over the period is the frequency. All right, so go practice all this stuff and you'll be ready tonight.